All right, now that we've talked about how to query an XML document via XPath, and then we talked about how to parse one, let's go forward and talk. All right, we're talking about our two essential perspectives here. We Let's go ahead and talk about the storing and retrieving part, right? We already talked about the XML as a DDL before, the notion of DTDs and schemas. That was one of our two essential perspectives. But right now we're talking about that storing and retrieving XML data as before. The import and export that worry about how to get data into a relational database, how to get data back out when it's semi-structured and defined by XML. Parsing helps. XPath is an option for querying it when we have it in document format. But now we have to think about the relational database specific situation. So let's return to that and talk about what our options are. First, I'm going to start with three options, then I'll talk about a few additional options that you have. One thing you can do is go back to our large objects we talked about and simply treat XML as a CLOB, right? A character large object. When we have that character large object, we have the X. This is a DOM tree that we have up here, and we can take that DOM tree and store it in its entirety. This is our DOM tree, and store it in its entirety inside of a simple table, and we'll just call it a XML store, for example, with its GUID, and just store everything as a CLOB, right? In that case, we're not really doing any parsing on input and output. So I'll talk more about that in a second. We can use it as a DDL, like we talked about before, a true data definition language, in which case we're going to parse the document, all right, and we're going to disassemble it into fine-grained relations and infer what the proper associations are between it. So we're basically doing that flattening we talked about to a relational structure by navigating down a tree, and we usually look at our XML schema for ways to do that. Or we can take a hybrid approach where we try and break it down somewhat, and the somewhat, of course, I'm fudging what I'm saying here, but there's a few different techniques for doing this that I'm going to talk about in this module, because it can get very interesting, and whatever you do, you wind up with a custom solution. So let's talk about some of these different alternatives. The first one, most straightforward, the coarse-grained approach. Take that DOM tree here. This is simply a different diagram of a DOM tree, generic, a root node with different elements and a subtree of the middle element. Take it and just put it all in a CLOB, right? In this approach, you just shove the XML documents into that large string area, that CLOB character large object. The benefit is we don't parse it in input, all right? So what I'm assuming is we've received it. We received it via an API, or we received it via some UI. Somehow it's gotten into our system, and we're intended to store it. All right, so I'm not going to parse it all. I'm not going to have this impedance mismatch of going between an XML document and a relational database. I'm just going to treat it as a big black hole, big black box, if you will. Now, if I wanted something out of it, and if I wanted to validate, and if that it conformed to a schema, if I wanted to verify it's the right kind of stuff in it, anything I'd want to do, well, I'd have to pull it back out, right? I have to pull it out of this table and go to this CLOB, convert it back to an XML document, and then I might run something like XPath on it or whatnot. All right, so in this case, the input case is very easy. The import case, I should say, because I'm just taking and writing it to a CLOB. The export, though, is very expensive. Not only do I have to chase down a character large object, which we talked about at the beginning of this module, can be expensive, but now I've got to pull it out, put it in memory, and parse it somehow. DOM, SAX parsing, run an XPath on it, run an XQuery on it to get whatever it is I want, no matter how fine-grained that information might be. Okay. I could go the other route. Instead of being very coarse-grained, just putting it all in a CLOB, I could be very fine-grained and say, I'm going to decompose. This is person and address over here, but maybe the person element is right here, right, in my generic DOM tree. But the whole point is I'm going to take this whole tree and I'm going to parse it down to each node type. And then I'm presuming that each node type has a relation that I can put on it with its different attribute types, and I can reconstruct the associations based on the associations I see in the DOM tree. All right, so I'm deconstructing. On this approach, it's very expensive on import, right? It's expensive on import. On our previous approach, right, this was cheap on import. This was expensive on export or on any kind of query processing, right? I pull it back out. This approach, the fine-grained approach, the opposite. It's very expensive on import because I'm deconstructing this whole thing. But now that I deconstruct it, now I can use my SQL tools that I'm very comfortable with and so forth, because I've completely addressed the impedance mismatch the other way by creating all these fine-grained relations. I may have some very verbose relational schemas, and I got to go through the process of flattening, which has that impedance mismatch as we're talking about. But the key is once I have it, I can use SQL to query, right? I could go. We're going to talk hybrid about how deep do I parse in this thing, and then how do I put information back together. I'm talking about a tree structure now. I haven't shown a tree here other than a parent-child relation to this one. But remember when we talked about, I have a tree structure that's very. I talked about a 5 deep tree, right? With more stuff in here versus a short fat one, right? A 3-element one. So with a bunch of stuff in the middle of the tree. So what am I talking about here? The deeper I go like this, the more decomposition I do. The more that if I start from some information and I want to reassemble an object that's been decomposed along some path in the document, the number of joins I have to do is proportional to the depth of the tree. In fact, it's not even proportional. It's exactly the same. Right here, I'd have to do 4 joins to bring back everything here. Well, I wrote 6 loops there. And I'd have to do 2 joins here. And joins are a very expensive operation, as we know. We do them, but we want to be cautious, all right? So we have to be very careful about how we would put together the original full information for what we conceptually would call an object if we've decomposed it down a path in the tree is the point. Okay. In a hybrid approach, we kind of do a little bit of both. There's a few different hybrid approaches actually I'll talk about. This is a generic one. If you look at how to flatten a generic tree structure, you can use this kind of relational pattern. Meaning, and this is basically, node here is the parent, right? And I can have a parent-child relationship where the child relationship is a foreign key back to itself, right? So I can have one parent for many child nodes. And so we saw this, for example, in fact, let me give a concrete example, perhaps it'll help. We saw this before with something like an employee, and some employees are supervisors or managers, let's say, right? So I may have a manager ID here, which is a foreign key back to the relation itself. All right, that kind of circular structure is actually the levels of a tree, where things are the same type. I can also have a branch off to the different attributes of an employee and maybe even different relations. Maybe employees do have departments, employees have names as complex attributes and so forth. And so I would take those things and make join and foreign key relations like we do in our algorithm. But this kind of recursive thing fits very naturally into a tree structure. Now, it makes sense as a tree structure when you have the same type of element. Here, when we genericize a node, right? All these things here, by the way, are nodes, is what we're saying. So we have them labeled in here of the different types they are, elements of different kinds and text nodes and so forth. But what I'm talking about is all of them from a DOM perspective, a W3C standard DOM like we talked about, are considered nodes. And from that perspective, I can serialize, represent every tree in this kind of parent child type relationship. But when I pull it out, right, what would I have in this table? I'd have a row for every single one of these. Every single one of these. So how many rows would I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'd have 19 here. All right. Different nodes just to represent the tree you see in front of you. Or maybe I could be smart and, take out some things that maybe are white space or whatnot and normalize it. So maybe I'm down to 14. But the point is they're all in that table. But how you would represent the structure then is I'd have foreign keys, let's say from this text node to this email to indicate that it's its parent. Right? And then specific values that are on attributes, whether it's, this is the content node. I don't really have this attribute over here for work. Right? I have a node for that, but the attribute value for work over here would be represented by the attribute table, which means for me to reconstruct a whole tree, not only do I have to join, but I have to pull in and join in the number of attributes I might have off of any generic node. All right. So this is since we know a well-formed XML document forms a tree, this can store any kind of XML document, no matter what the grammar is, representing the DTD or the XML schema. Since it's generic like that, that's its benefit, right? I can apply that pattern to any XML document. However, I'm representing things now as node and attributes, right? I'm back to that W3C thing I talked about again, meaning I don't know, where's the typing information going to go? Where am I going to know it's a text node versus an element? Where am I going to know the value or the subtype of the grammar is email versus address? Well, I'd have to put those on columns on my table, right? Which means for me to actually get type information, I'd have to runtime look it up. I'd have to recreate the tree or subtree, and then I'd have to look at a particular column and say, oh, the type here is a type of element that holds the address. And I'd have to look at that information so I'd have to know how to navigate, to traverse the tree to find the semantics that I want. So this kind of takes away a lot of typing information. And every time we take away that typing information, we're kind of lost now. We've lost our semantics and we've got to go through something to recover them and get them back. And that can be potentially very expensive, right? I mean, classic problem, right? Anytime you make something more general purpose, you're losing specific information that you can take advantage of to turn around and make your code more efficient, work faster, work in a more application or domain specific way. You can bypass, by the way, right, the marshalling process and marshal through an intermediate format. In this case, here shows an example marshalling through Java. I can do object relational mapping like we talked about with JDBC and go from the things in the XML document in this case over to Java. So this is an XML this is an object to XML mapping, if you will. But once I have that, then I can go through my object to relational mapping to go from the object to relations. Okay, so I basically can make it a two-step process, which may work if I've already done this. All right, and again, so we saw some of that when folks were basically doing, this. They were going from relational schemas to databases, from databases to objects, and they were just completing the loop. I wouldn't say that this is tremendously efficient. It's really trying to leverage a set of domain objects that you've done before and trying to abstract away the details of whether or not it's XML based or relational based. So let me state that a different way. The only times I see this anymore is when an organization has to starts with the object format as its type definition for its domain. All right, so think about that. You're an application or a systems program, whichever, and you're doing domain modeling like you talk about in 3.15 and 4.15. We're just trying to understand the objects in the vocabulary of a domain. At some point, you want to make that tangible. You're actually taught in this curriculum several different places you could do that. You can do that with an ER model. You can do it with a relational data model. You could do it with a classic data dictionary in natural language. You can do it in XML now. You can do it in JSON. You can do it as a programming language construct, and particularly in a strongly typed language like Java, right? That could be your canonical representation, right? You can use UML. Okay, but this can be your representation. If that's your representation, then chances are you're going to start building marshalling or conversion formats in different directions to the types of things you need to use behind the scenes. Maybe you got to marshal it to an XML document type model in order to exchange it over an API. Maybe you do the same thing with JSON. You might have to marshal it in this object relational world because you need to persist it, and your persistence still remains relational databases. So this notion of conversion, of marshaling from something to another, very often you got to pick a canonical and origin format that you represent your data in, and then you start looking for mappings between those different things. So all I'm saying is once you have that, you can start chaining those things together and going from XML to objects over to the relational model. And you want to do that without losing any information. That's the main thing you're after. The benefit of that is you may already have to do that anyway, right? You may already be doing these things. So therefore, hey, you already got a set of domain objects. So I'm just leveraging code. I'm leveraging understanding that I already have and design I've already done from a domain perspective in my system and in my organization. The drawback is anytime I add another layer like this, right, I'm going to be slower. I've got more code, it's more layers it's got to go through to get to the format I want. Maybe I really want it in a database, maybe I really want to go from the database to here, but now I got to go through an intermediate format, and of course that's going to take slower. That's just the nature of the beast. There are other options, right, other than the three I've just talked about. there are database extensions. So what happened was, as XML became popular, again, late 90s, early 2000s, database vendors started coming out with some of their own native support for XML. Just another example where vendors are getting away from the SQL standard and trying to do vendor lock-in by creating their own ways of supporting XML in their database, right? If you were an Oracle person, you had a set of Oracle types and Oracle navigation facilities for dealing. If you were a Postgres person, a different one. So finally, the SQL standard got around to its next extension. We had SQL 92, we had SQL 99. SQL extensions in 2003 and 2006 added some XML things, if you will, to the standard, and you could start using them wherever you use SQL types. Here's just an example of things. So you had the XML type, you had these different operations that would work on them. You could do an XML parse from a SQL string. You could do an XML serialize, the opposite, XML root, ask whether something is, the XML type is a document or not, or just a fragment. You could produce an XML element from a SQL expression. You could produce an XML attribute, and so on. And then SQL 2006 added some even more predicates and tests to that. And SQL 2006 also provided support for XQuery. Again, not going over XQuery here, but an example of a query language in SQL 2006 would actually allow a second query interpreter, query executor, to be built into your relational database and leveraged through SQL extensions defined in the standard. All right. Folks are also doing extensions. I mean, so that's the standard. People were doing extensions back in the day. I remember when Oracle built in a JVM right into their server, and I do remember doing things like actually building an XPath interpreter directly into the database, so you could submit an XPath query directly to the database server and have the database server execute it for you. Because remember, we're talking client server, your application code, server over here. So before, we've kind of assumed that you're going to pull out this XML, ship it over to the wire, put it in the client space. The client space is going to DOM it up and then go do an XPath and find what you need. Now we're saying the client could send a query over and this XML will be DOMmed up over here. So then the XPath could be executed this way and only the results would go that way. Certainly more efficient. So you'd see all these kinds of things going on with database extensions, standard and vendor proprietary, to deal with XML in a SQL world. Here's an example, right? An XML element used as part of a select clause. Select e.id XML element from name employee, XML element name, first name or last name, XML name dependents. Select star from dependents D where as X value. From employees where some filtering clause. This kind of big long nested query. What would I get back? I get back an XML element. I mean, look at what it's returning. It's got an ID value and then a fragment of XML because that's what I told it to name, and that's the kind of things I told to put in it. All right, this from this, the name of the dependents, that's the name of the element, from the count, all right, of this nested clause, right? So it basically said this is what I'm going to return as the value of the select clause. So the server's already done the work. So if you were just going to turn around and share that, right? If your application, I just talked about client server, if you're going to send that and your client was actually working with other B2B interfaces to put together a higher order solution, it could basically ship that XML across the wire without doing any of the marshaling itself because it was already done over here. Right? And anytime the conversion is done closer to where the data is, it's going to be more efficient. JDBC4 introduces things like a SQL XML type. That corresponds to the SQL standard that it asks for. And again, it will allow a client app to deal with XML in whatever way you want it. String stream, or what's the SACS event stream, like the SACS parsing would actually serialize the event stream for you. An advanced JDBC feature, we're not going to do it in here, just mentioning that as you came up with SQL standards, something like a low-level plumbing standard like JDBC would follow right along. All right. The question next is, once you have this kind of, once you make kind of some alternatives, how do you determine which way the best? Well, of course, the best always depends. And I know that's not a great answer, but there isn't one way to do it. You really have to have a set of guidelines or heuristics for making such a decision. So some of the things I would think about if I'm worried about storing and retrieving XML from relational databases, well, first I want to know is your database simply a backing store for persisting and moving XML documents? Use the coarse-grained approach, meaning if some folks kind of use your database as almost a shared file system, and now there's better shared file systems approaches, but a way to just store entire documents. If I don't need fine-grained information, shove the whole document in the database, let it track it, let it be persisted, archived, and so forth under your data management processes. And when somebody needs the whole document, you pull it out as a cloud and you turn around and just send it off to whoever is using it, because you're not worried about the processing of fine-grained data. If you have one or a small set of DTDs or XML schemas, really, that support with rich metadata, then use a finer grain approach. Rich metadata means I have a lot of good descriptive information. I have a very detailed schema that tells me what the semantics of things are, and I really don't want to lose all those semantics. So I really want to go down and parse that deep tree, right? Meaning I've looked at the structure of a deep tree like this and said, yeah, it's deeper and everything, but this is a lot of good metadata as I go down different levels. That's a rich structure, and I want to keep that rich structure and not lose it. All right. If I do that, then I do want to have a fine-grained approach. I do want to have different tables for different entities. I do want to parse recursively down the tree and put those things in those one-to-many relations you're going to wind up having when you decompose a tree, because that's the way, that fine-grained way is the way I expect to use the data, so it's worth that expense on import. If your XML really represents serialized business objects, then do something like an OR mapping, and that's the case again here, where if I'm already doing this kind of activity where I'm serializing between a relational database and objects, and XML has come along as a new thing, JSON has come along as a new thing, then I'm not going to get rid of one of these layers, and I might be able to leverage the fact that this is already here. I've already built those objects, and I can leverage that even though it's more inefficient to go through an extra level. At least I know I'll have fidelity across those layers. Right? But the biggest thing I would say, my biggest tip is here, and not enough folks do this, and it's something we talked a little bit about with query optimization. When you're using a database, we talk a lot about data modeling from the perspective of what is mathematically elegant, what's in a normal form, it represents functional dependencies, because that creates an extensible data model for us. But we also have to think practically, how is our data going to be used? And when that's the case, we have to think about what our XML document structure is, but also how it's going to be queried. Right? When I query information out of an XML document stored in a relational database, however it's going to be stored, do I have to assemble information from some top-down way? Am I working across the tree? Do I have top-heavy metadata and so forth? So I want to talk to you about this last one because I really think this is the way I think about it, and I don't think enough data modelers, if you will, that I've come across with that have worked with XML think about it this way. Think about where the typical queries are going to be. Are your typical queries going to be path oriented, like an XPath, right, from the root node all the way down to some leaf node? Is it going to be the opposite, where it's top heavy, meaning it's only dealing with a few nodes at the top because they have all the rich metadata, and this is really maybe just a whole bunch of text or a whole bunch of relatively vanilla information that's totally describable what's in the upper layers? Is it something across the tree? Right? All the things in a certain layer represent something. Maybe that's all the addresses. Maybe that's all the siblings. Maybe that's all the whatever. All right. Or do I have a query pattern that really kind of is random? I got nodes at different levels, not related to each other. Right. One is I might want to look and say, is this a good design at all? All right. And is there a way to remodel my XML and rewrite my schema to put these things together? Because I will tell you, these cases, 1, 2, and 3, over here, if I can identify those structures, it really helps me heuristically, guideline-wise, to really understand how I want to deal with this data. All right, I should know how often I'm writing or importing, how often I'm exporting or querying a structure, and I should know where the typical types of queries are going to be executed. Doesn't mean all of them, but I mean the typical ones, the one that I'm going to use most often, the ones that have to execute the fastest. All right. Once I have that, then I can understand. So I'll give you an example. My team built the Virtuoso Delivery Engine, which was a content delivery and assessment engine for the Cisco Networking Academy years ago. And we did it all in XML. And we got a bunch of e-learning content in XML. And we also got a whole bunch of assessment tests in XML. And our goal was to render personalized learner content. Basically, we knew something about the learners, so we'd make some very intelligent decisions about what content they were supposed to get based on how they were doing in these different assessments. So we'd actually see a tree where we'd have rich metadata at the top of it. All right. And that rich metadata allows us to make a lot of decisions about that content and those assessments that that particular student was supposed to get. So we put the metadata at the top. All right. So we did that so we could treat a lot of the data down here in CLOBs. Right. It helped us filter quickly at the top and keep this even in memory if we wanted. All right. So then we could decide what big data we need to get and deal with, because we would be dealing with that document, if you will, throughout that user's experience, that individual's experience. So we'd pull it out less often, but all the data we needed associated with that student, if you will, the Networking Academy was there. All right. We actually fully parsed and stored assessments because they had a rich set of types. So this was content model we referred to, the assessments will refer back to it. And then we took grading criteria and actually put it in serialized objects. So we actually had binary large objects that represented binary data that was actually compiled code that was associated with those objects. So it was really a combination of some of the different techniques. It was part hybrid, part selective use of a CLOB, again with fine-grained information at the top of the tree. So we even combined the first three techniques we were talking about in order, because we knew how we were going to use that data and what the true scalability things were. We shoved data into this thing only periodically. We had very infrequent writes of content, frequent writes of assessment results, frequent processing of assessments, and frequent exports of CLOB level data that we could then parse and extract the information and use it all during one user session. Right? Those happen to be our requirements. I'm not saying that's how you do it, period. I'm saying for this particular set of requirements we had to build an e-learning platform, that was how we did the design in order to understand and minimize based on the expected query patterns. So there's no one right way, I'm saying, out of the different options I've given you here. You have to know your requirements. You have to come up with a design that'll satisfy those requirements. You should track your query patterns over time, just like you would do with a relational database, like we talked about in query optimization, and see if you need to restructure your XML or restructure at least how you're storing your XML and retrieving it in order to optimize your performance. Okay.